Yeah, it works. We see the slide.
Okay.
Thanks. We will talk
Great.
about gauge two-form symmetries in 60 SCFTs coupled to gravity. Please.
Great. Yeah, thank you very much. I also, of course, thank a lot the organizers for giving me the opportunity to speak about my work. And this is some work that that happened here together with Magdalena Lafors, also here in Uppsala, and Andreas Braun from Durham. And then also at the end, I will talk a little bit about some well, connected work that appeared recently together with Finn Kohl, who was a master's student here in Uppsala. Okay, so the topic of my talk is essentially how these relatively new considered symmetries, namely higher form symmetries in this particular case, two-form symmetries, how these guys actually play together with gravity, six-dimensional gravity, because from our standard quantum gravity law, we know that in principle, if I have a symmetry of some theory, like a global symmetry, there's only two fates that they can have. It can either be broken or gauged. And this was exactly what we wanted to look at in this work. Okay, so first so this is my outline. I will first have to review a little bit what higher form symmetries and 60 SCFTs are. Then I will focus on the two-form symmetries and how they behave when I couple them to supergravities. We'll spend some time with some examples, in particular examples with a lot of supersymmetry, 2,0, six-dimensional supergravities. And then I will also give an example with a 1,0 supersymmetry in 6 dimensions. And then, of course, I will summarize and conclude. Great. So let's maybe give a lightning review of what a higher form symmetry is. And for that, it's always best to sort of remember what a zero form symmetry is. So if I have a zero form symmetry in d dimensions, as it has been generalized and worked out by Gayotis, Seiberg, Kapustin, Willett in 2014, then you have for a continuous symmetry a d-1 form current J. You have some operators U that is supported on some d-1 manifold G, and that this operator itself satisfies a group law. So if I take two of these operators UG and that are supported on the same manifold, then I can compose them together according to this group law here. And the point sort of is that if I take those and I have a certain operator, like for a zero form symmetry, a point operator, which is well supported at a point, and I surround that with some symmetry operator, which should then be a d-1 sphere where this point is in the middle, and I surround that, and I then pull out this symmetry transformation and I contract the sphere, I will get a phase. So that is the normal story of a zero form symmetry as we know it. So then for a higher form symmetry, you essentially just extend the operators onto which these transformations can act on. So now you have a p-form symmetry in d dimensions, which if it's continuous has a d-1 p form current J. And you again have some symmetry operators U that are supported on a d-1 p dimensional manifold. I still have this group law in the same way as before. And now I have some operators that are supported on p-dimensional, well, subvarieties of my manifold, and I can essentially do exactly the same. I surround these guys with my symmetry transformation, which is supported on a sphere, on a d-1 p sphere that surrounds my p-dimensional object in d dimensions. And if I pull it out and contract the sphere, I will get a phase. So that's essentially the story of the higher form symmetries. And of course, the cool thing is that I can use all these technology even if I don't have a current. Yeah, if my group is just discrete, which actually, in fact, will be the case in most of the things we're going to look at. And I don't have to have a Lagrangian description of all of this. I can really just deal with these operators here, and then the actual operators that these that these symmetry transformations in the electric case will act on are, for the one-form symmetry case, are going to be Wilson lines, and for example, for the two-form symmetry case, can be Wilson lines. Wilson surfaces. Good. So now I have to switch gears, and I have to consider 60 SCFTs because I want to look at the specific symmetries that these SCFTs have. And so 60 SCFTs are, well, sort of theories that are very special. They are super conformal field theories that are living in the maximum amount, the maximum dimensions, and it has been shown by Seiberg and Witten that these are theories that are necessarily strongly coupled and that they admit tensionless strings in their spectrum. So these are theories that are necessarily not Lagrangian. Great. So now we can what we can do is we can engineer these theories geometrically. So although we don't know the Lagrangian, we can engineer them geometrically, which is sort of the nice thing about string theory. And we do it by taking type 2B strings and wrap and compactify them on such a complex two-dimensional base as is given here. And this base looks like a bouquet of P1s with a certain self-intersection. And the point is that in type 2B strings, you have D3 branes, and these D3 branes can wrap these spheres here, and they essentially wrap these internal part eta here, some cycles, some 2 cycles, and a space-time cycle C2. What the D3 branes wrap, and they give therefore rise to strings that have a certain string tension, and the string tension goes essentially with the volume of these P1s. And if I shrink, or if I'm able to shrink all of these P1s to 0 size, I essentially eliminate all the scales in my theory, and I get a super conformal theory, and these strings become tensionless, and these are the aforementioned tensionless strings, and that I have in 60. Very good. So these cycles eta here, they live in a certain they wrap certain cycles H2, and the cycles they wrap actually span also a lattice, which is the string charge lattice lambda s, and this string charge lattice is sort of important for the following reasons. So like I said, I have the string which wraps this space-time cycle and this internal cycle eta here, and if I write this 2-cycle eta in terms of a basis, well, which I can do, of course, I will just write in a basis of my H2, and these basis elements here they define me a certain intersection pairing geometrically, which you can identify with a Dirac pairing. So these basis elements eta I, they define for you the geometric intersection pairing omega ij, which up to a sign corresponds to the Dirac pairing of the pure theory. So now these 6D strings that you have, they naturally couple to the two-form fields Bi that you get. And you can see this directly from the Kaluza-Krein reduction that you do when you take this D3 branes that wrap these cycles here and do the KK reduction. So then you just integrate over this space-time 2-cycle, and then you get this internal coupling here where this AI omega ij is essentially the string charge to which these strings couple. So now, since you have these Bi, you can use the field strength of that to essentially define a two-form symmetry transformation. And the symmetry transformation parameter I call lambda I. And if you write it down, the way it works is, and here I use as my manifold a 3-sphere, it's going to be some exponential which goes over the symmetry transformation parameter and then sums over all the different Bi generators that I have. And then I integrate over its field strength. So very good. So I have the symmetry transformation, and now I can look what kind of gauge transformation I have if I surround an operator that is supported by such a two-dimensional string here. So if I do it, I just do what I had before, and I will essentially get a symmetry transformation like this. Yeah, so this is essentially, remember, this part here is sort of your string charge, and this is your symmetry transformation parameter. Okay, so if I do this, you can obviously see that in general, I will get a phase. And so this essentially tells you that as soon as I have some strings in my spectrum and I have such a symmetry transformation, which gives you a global two-form symmetry, at least naively, then these non-trivial charges that I have here, they break your two-form symmetry completely down, at least naively. So that's what these strings are doing. But now you will actually see that there is a certain remnant symmetry that you can still write down. And the way you can see it is if you essentially rewrite this phase factor here, which is in Z, and you write you rewrite essentially your symmetry transformation lambda I times some eta I. So here I just rewrote the intersection pairing into a geometric object, namely gamma is now identified with some element in lambda S. And this dual piece here, which is essentially the cycle that is wrapped by the string, lives in the dual string lattice lambda star. So the point is now, if you rewrite it in this way, you can quite easily see that there is an additional remnant discrete symmetry under which these strings transform trivially. And this discrete symmetry, or this remnant discrete symmetry of this U1 to the R two-form symmetry, is essentially measured by this discriminant group here. So as long as the charge lattice lambda S is not the same as its dual, so if this string charge lattice is not self-dual, then you will get some discrete group that you have here. And this discrete group is also known as the defect group. And it has been, well, considered in various works, and there's various ways, and there's also how to compute it. Like, for example, nice ways to just compute the Smith normal form of this intersection pairing. And it has to do that these SCFTs essentially have a global discrete two-form symmetry. So very good. So now we have these SCFTs, and now we want to somehow want to incorporate them in the supergravity theory. And this is actually something that happens extremely natural and very often. So in many of the recent supergravity literature, you will actually see that SCFT sector or E-string sectors and whatnot, they naturally appear in your SCFTs, in your supergravity theories. And they are actually also very important to connect the whole landscape of, the whole landscape of 1,0 supergravity theories that have different amount of tensor multiplets. So in order to connect all these different theories, you will always go to some sort of SCFT point. Very good. So now we can essentially follow the same strategy as before. So you take type 2B or F-theory, compactify this on a base B, which is now really compact. And it also has a string charge lattice, which I call lambda B. And you will have essentially the same story. So there are the three branes that wrap some curves, eta, in B, and those will lead to 60 strings that have a string tension, but you can make them tensionless when you choose to shrink a certain sublattice that is embedded in your compact string charge lattice. So of course, as I just told you, one of the, well, actually 60 SCFTs can in principle have a huge amount of global symmetries. And one of them being these two-form symmetries that I just told you about. But there is this common quantum gravity law that now that these SCFTs or this subsector is living in a gravity theory, the global symmetries can essentially have only two different fates. The global symmetry is either broken or gauged. So that's our expectation. And of course, what we want to focus on now are these two-form symmetries. So what about those guys? When are they broken and when are they gauged? Or can I maybe, well. And so let's maybe first look at if you can have global symmetries. So if you want to look at this, you first have to note that this string charge lattice that you have for a 60 supergravity theory is highly constrained. In particular, it must be unimodular and self-dual. Now, this has been also shown by Seiberg and Taylor a couple of years ago. And from that, it directly follows that this naive discriminant lattice that you take, yeah, lambda B star over lambda B is equal to 1 because it's the same, it's self-dual. So that's very good. It tells you that there are no global symmetries. And but you can actually also look at this very concretely. If you take, for example, 1,0 theory, then the minimal model program has taught us that the basis that you consider can only be P2, Hilsebroch ends, or generic blowup of these guys. For those two bases, you can compute easily that the two-form symmetry is trivial. And then if you just take generic blowups of those, so you just add -1 curves essentially into the base, then you also know that these -1 curves, because the determinant essentially of these guys is 1, do not add any two-form symmetry. So that essentially tells you that all of these bases must have a trivial global two-form symmetry. But I mean, this is sort of already clear with the statement that lambda b must be unimodular and self-dual. Okay, so no global two-form symmetries in the supergravity theories. That's good. Yeah, things are consistent. But of course, there's another possibility that you can have. So now we know that the global symmetry is absent, but maybe it's a bit more interesting to look at the gauged form of these symmetries. So how do we do that then? So what we actually require in order to do that is a gauge transformation, gamma, which we have assorted with these geometric object, under which all the strings in our spectrum have trivial charges. Okay, we want to have a non-trivial symmetry transformations, but in order to be gauged, all the strings must have trivial charges. So then what we do is we have to start by taking some 60 SCFTs that come with their string charge lattice lambda s, and we have to somehow embed that in a consistent way into our compact string charge lattice of lambda b. So then all the strings that are living here, they can have by themselves, just by themselves, without being compactified, they can have a two-form symmetry. And these two-form symmetries will essentially be just the product of them. So for example, I can take 3 SCFTs all by themselves, and these 3 SCFTs will have all by themselves a two-form symmetry, but now I want to take them and put them into a compact geometry. And I want to do it in such a way that there's an overall symmetry transformation, gamma, that acts trivially on these on the charges of these strings there. So that essentially means that I'm requiring that the cycles, the 2 cycles that the strings wrap, cannot be in the string charge lattice of the SCFTs, lambda s, but only an n multiple of them can be. So geometrically, that means that I can find this generator here, which I call, and the group I call G, precisely if the intersection of the dual of the string charge lattice in the base modulo the string charge lattice is in Zn. So that is precisely the condition that I'm having. And you can actually rephrase that a little bit. And it simply means that the SCFT lattice that you have chosen to take, where you compactify your SCFT sectors, must be non-primitively embedded into the compact string charge lattice. And that means that essentially this discriminant lattice of the compact string charges lambda b modulo the SCFT lattice lambda s must have a non-trivial torsion piece. So this is essentially the abstract way of formulating this condition. Let's now look at a couple of examples how you can actually see this. And the simplest example is, of course, type 2b strings on a K3. So this gives you a 60 n, 2,0 supergravity, and this supergravity theory actually has a unique string charge lattice, which is gamma, or which is an even self-dual lattice, of course, of signature 5,21, and it can be decomposed into these factors here. Okay, so maybe it's a bit of a surprise that there are 2 additional pieces of the hyperbolic lattice U inside here, but these essentially correspond to the transformations of the B2 and the C2 field and the self-duality. Whereas this part here is exactly oh wait, there's an u to the 3 missing, sorry. This part here is precisely the lattice of the K3. So this is the lattice, the string charge lattice that a generic 2,0 supergravity theory has when you put type 2b on a K3, but it can also be non-geometric.
You have 5 more minutes, Paul.
Very good. And of course, now what you're doing is now you choose an SCFT subsector, which for a 2,0 case means that the string lattice must be a composition of ADE, lattices gamma I, and this you have to now embed into this non-primitive way. And then, of course, the two-form symmetry you get is precisely this quotient that I just told you about. And actually, how to do it in a very systematic way has been shown last year and this year by Font and Freiman et al. By essentially simply classifying or studying ADE embeddings that are non-primitive into this Narayan lattice, which is precisely gamma 5,21. So if I just take, for example, this algorithm, I can study all kinds of non-primitive embeddings of these ADE sublattices into gamma 5,21. So this would be a direct way how to do it. Okay, let's now assume we have done that. Now we did so. We find some SCFT with a non-trivial two-form symmetry that I have here, and I will call this SCFT sort of gamma I mod G. Yeah, so I have done it. So how can I see that this is sort of what is happening? And what I can do is I can compactify this theory on another circle. Because if I compactify a 2,0 SCFT on a circle in 5D, I will get a 5-dimensional gauge group of the same ADE type as the SCFT in 6D. And moreover, the two-form symmetry that I had in 6D will reduce to a one-form symmetry. And you, of course, expect the same thing to hold true for the gauging. So what we expect is that in 5D, upon the circle reduction, we will get a non-simply connected gauge group, which is of the same type, the sum over gamma i's mod G. So actually, you can test this. You can test this because the circle compactification coincides with M theory on the same K3 times the circle. And there you can use this distortion condition that I just told you before to explicitly verify that the group should be of that form. Actually, if you just assume a tiny little bit more, you can check this proposal even further. So let's now assume that the K3 that you start with is also elliptic. If you do so, that means that the Picard group of the K3 can be decomposed in one of these hyperbolic factors, which essentially amounts to the section at the base and this so-called frame lattice, which is essentially all the divisors that do not intersect the zero section. And then I choose my SCFT lattice to be inside this frame lattice. And if you do so, then you can actually reduce the condition of this two-form gauging to be precise, precisely coincide with the torsion model Y group that you have to have in order to satisfy the condition that you have a two-form gauging. Now, so if you want to have a two-form gauging and you want to be elliptic, then one choice essentially is to choose a model that has a non-trivial model by torsion group. So very good. So now our K3 is also elliptic, and you have M theory on this T2 times K3. But since it's elliptic, it also means that I can lift it to F theory. So I can essentially lift this T2F that I have here, and I can lift the torus vibration that I have inside the K3, and I can lift it to some 8-dimensional theory, which also should exhibit precisely the same non-simply connected gauge group. And that this is precisely the case, of course, has been shown by Aspinwall and Morrison many years ago, and that these theories are actually consistent, so that this non-simply connected gauge one-form symmetry in 8D is consistent, and therefore also the 5D version has been also shown very recently by Miriam, Marcus, and Ling and Hao. So very good. So this is a very strong evidence that the two-form symmetry in 5D is consistent, because it can come from an 8D non-simply connected gauge group, but at the same time it also comes from a gauge two-form symmetry from when I'm lifting to this other vibration, essentially, or to this other 6D theory. So then, of course, you can essentially do the same game for 1,0 theories, and the game is essentially the same. And the way you have, of course, many more possibilities. The SCFT lattice that you are choosing does not necessarily have to be of ADE type. You have non-Higgsable clusters, higher self-intersecting curves, many more possibilities. But the upshot essentially is that as soon as I choose a base that you can write as a global quotient of some element theta here that has fixed points, and my SCFTs comes from these fixed points, then I will also have a two-form gauging which coincides with the order of this global quotient. And of course, I mean, there's a lot of nice examples, and the simplest example you can write down, I'm almost done, is that you take a toroidal orbifold like this. And this is the work I have done with Finn and Magdalena a little bit earlier this month. And you just take such a toroidal orbifold, since you have a torus here, you can, of course, always take an F-theory lift. And for this very simple Z3 quotient, what you find is actually that you find 3 times 3 times 3 twisted sector fields. And if you take this here as your base, and the base is precisely a T4 mod Z3 quotient in a non-crepant way, so it will give you 3 times 3, which is 9, minus 3 non-Higgsable clusters. And each of these non-Higgsable cluster has a Z3 two-form symmetry, but it's precisely embedded in such a non-minimal way that there's one diagonal two-form gauging that acts, well, diagonally in all of these sectors. So very good. This brings me to my quick conclusion. So essentially, you can gauge two-form symmetries in 6D supergravity theories when this condition here holds. So when the SCFT sector is not primitively embedded into your base, you can do many nice things, and you can compute many things also very explicitly. And we also want to do a couple of more things. For example, you can, in a toric fashion, you can classify in a very nice way all the toric bases. And actually, you can also classify all the orbifold bases that are toroidal and compute the two-form symmetries that are possible. But another very nice thing, of course, is that that there is a holographic dual that you should look at, which is given by, well, the holographic dual to the strings, which is given by ADS3 times S3 mod the space that I was looking. And it would, of course, be very exciting to see if this two-form gauging that I was just telling about will somehow affect the holographic dual that you can look at. And yeah, I guess with that, I will conclude.
Thank you very much. Are there any questions? If so, please raise your hand. So maybe I can start. Is there a way you can understand these two-form symmetries in 6D already from an M-theory construction? So we know especially of M-theory constructions of n equals 1 or n equals 2 SCFTs. Mm-hmm. So is there a natural way to discuss them, maybe not in a gravitational, but in a local model from the M-theory perspective?
Well, I mean, so in a sense, yes. In a sense, that's actually something we used in this 6D to 5D duality picture. So I mean, this is actually geometrically the way you would do it is using the methods of Sakura and Del Sotto et al. Well, the paper by, I think it was Willett, Sakura, and Morrison from last year or the year before. And you can use to, for example, already compute in 5D in M-theory on a Calabi-Yau. You can nail it down and compute the two-form symmetry. Or well, in 5D it would not be a two-form symmetry, but it would be a one-form symmetry. You can compute the global one-form symmetry from the local geometry. Absolutely. And then you can make an argument that, okay, I have maybe an elliptic vibration, I'm able to lift it to 60, but the contribution from the one-form symmetry sort of sits in the base. And then you can do this argument that I just did before, that it's actually a circle reduction of a two-form symmetry from 60 on a circle, and then it becomes a one-form symmetry, and that's the one you just compute it essentially.
Okay,
So
I was more referring to the construction as like the world volume theory on M5 brains, but I see that Craig has another question, so maybe let's listen to his one first.
I don't know. You can also finish the previous question. It's but okay. Let me ask then. So this is, I guess, a fairly straightforward question. So I also know which kind of 60 SCFTs can and cannot be coupled to gravity in the 1,0 case based on basically the tensor branch rank of that theory.
Yeah.
So do you see, I mean, is there some way to get similar numbers like the, whatever it is, the 492 or 496 or whatever, from studying these kind of two group symmetries?
The two-form symmetries. Yeah, I would hope so, but unfortunately not. So it's, I mean, it's essentially I guess you're asking if sort of, if from a symmetry argument, I can see already what is the highest number of tensors that I can have in a 60 supergravity theory, right?
Right.
Yeah. I mean, I have not seen it, unfortunately. It's more that you still do the other way around. You take everything, that all the bases that you know, and then you sort of check when I can have a two-form gauging as a limit for those that are possible. But I mean, of course, it could be that there's maybe a nice mixed anomaly or an argument like this that you could study, and I haven't studied it, but it would be very interesting.
This would be my question. Like, is there a physics reason for why, you know, you're restricted to only the bases which mathematically exist rather than the other way around? But I see it's not known. Okay, very good. Thank you.
Yeah.
Any other questions?